Hi everyone, I'm back. After the Cerberus project has been concluded, we very recently released release 1.2 of the Cerberus board, which is most likely is the final release, since the delta between 1.2 and the original release 1.0 was so small already. Anyway, I don't think there is much left to improve. So this is it, release 1.2. The idea of this series of short videos is to give you an introduction to the final design and demonstrate some of its capabilities to you very briefly without going to any design details. What I will do now, only in this first episode, is to just give you a very quick overview of what you are seeing here on the main Cerberus board. It's encased in two standard plates of plexiglass. These are micro ATX trays. I didn't cut them, I didn't drill them. You can just buy them on Amazon. And the board within is also in the micro ATX format. And what you see here is the following. This computer can be divided in two parts. This part here going up, that's the video generation part. From these two large chips up. And from the same two large chips down, it's the computer proper. These two large chips are the video memory here and the character memory. They are both dual-ported memories, so there are ports that give access to the video side and another port that gives access to the computer proper. So via this dual-port construct, the computer proper can interface with the video circuitry and display something via VGA. Now, this is Cavia, one of the three custom chips in Cerberus. It's a 5-volt CPLD. And this basically scans the video memory and then the character memory to produce the video signal. This is Skunk. It produces the clock for Cavia. It produces the sync pulses for the VGA signal. And it reads out, ultimately, it reads out a byte at a time from the character memory, stores the result in an internal shift register, and then shifts that one bit at a time out to the VGA signal. And that's how the video information that you're seeing to the left is generated. Now, this chip in the middle here is just a buffer. It's just to strengthen some signals. This is the oscillator for the video circuit, 25.175 megahertz, which is the standard VGA frequency. Now, on the other side of the video and character memory, we have the computer proper with two CPUs. This is a 65CO2 CPU, and this is a Zilog Z80 CPU. We also have an I/O controller, which is an Atmel Atmega 328, the same chip that is in the Arduino Uno. This is also just a buffer, like this one. This is just a buffer to strengthen the signals. This is the 16 megahertz clock that governs the computer proper here on the lower part. And then we have two chips for SRAM, each one 32 kilobytes. Combined, they have 64 kilobytes, 60 kilobytes of which are user accessible. The other 4 are allocated to the video and character memories. So you have actually 64 kilobytes of addressable RAM in this architecture. And there is no ROM. And you might ask, well, how come? Where is the kernel? Where is the BIOS? The BIOS is in the internal flash memory of the I/O controller, this Atmega chip here, which has a Harvard architecture. So the address space is divided between the usual address space for data and the memory address space. So putting the BIOS in here does not use up any of the system address space. So everything is available. All the 64 kilobytes are available to each of the 8-bit CPUs. Now this chip in the middle is Spacer. It's also a 5-volt CPLD. And this is the maestro of the entire system here, of the computer proper. It's what glues everybody together. It's the controller that binds everything together. It also has a number of internal shift registers to allow this I/O controller here, which we call CAT, the custom Atmega, to allow CAT to interface to the parallel buses, because these controllers here, they do not have parallel data and address buses like the CPUs. They do not have 16 plus 8 pins for the buses. It's all serialized. So it communicates serially to spacer, which then parallelizes it, and the other way around. So in a nutshell, that's Cerberus. The idea of Cerberus is that it's an educational platform. All the custom chips here have been designed at the gate level without any high-level synthesis tool. So they illustrate very, very much detail how an 8-bit computer, and in this case even a multi-CPU one, can be constructed. So the idea is to make computer design accessible to everyone, serious hobbyists and students of computer engineering. Now, the VGA video, it's done in the old-fashioned way, which is actually more difficult than if we go just for colors. The old-fashioned way, which was used in the late 70s and early 80s, was using a shift register, and that had to do with the performance and memory constraints of the time. So I tried to replicate that as a sort of introduction to computer architecture. It's black and white, character-based, but all 256 characters, the definitions of which are stored in this memory here, the character memory, they are all redefinable on the fly. So you also basically have graphics, and I will show that to you in one of the future episodes, how you can build a high-resolution graphics just by on-the-fly redefining the character definitions. But standard out of the box, as you get it from the repository, that's what I will show you in this first episode. This is a little micro SD card inserted here, which contains the code we will run today. It also contains the standard character definitions that are loaded up in the character memory during boot. So the system can display something on the screen, as you can see here to the side. So let's have a look at what it does. So this is the boot screen. On the top part where you see the three-headed dog icon, that's where what you are doing will be displayed to you. And the lower part of the window, that's where the prompt is, where the cursor is. Now Cerberus tells you immediately what mode it is in. Right now it is in a 6502 mode, so it's using this CPU instead of this, and at 4 megahertz. We can speed it up, we can type fast, and then it will go to 8 megahertz, as you see there. We can go back to 4 by typing slow, and we are back to 4 megahertz. We can also go to a Z80 mode. So if I type Z80, it's now in Z80 mode at 4 megahertz, and we can also go to fast Z80 at 8 megahertz. The list of commands is available if you type help. So they're all displayed on the screen. I will go over them very quickly with you. We can also, if I clear the screen, you can also call for help by just typing an interrogation mark, and it displays the commands there to you again. Cerberus has a soft reset, so you just type reset, and it will reset itself. So there is no need for a reset button because the I/O controller is fairly independent of the rest of the system. So even if the CPU gets stuck somewhere, you can still soft reset Cerberus. So let's run some basic applications. The system has a built-in file system. So if I type dir, we get the files that are currently present in that micro SD card. There's a lot of Cerberus stuff already in here, some basic programs. .bbc is BBC basic code. I will illustrate all that to you in one of the future episodes. Today we will do something very simple. I will load a basic application. Type, I'm in Z6502 mode now. So I'll load this typewriter application. It's in memory now. If you want to see what's in memory, you just type list. And by default, list will start from address 0 and show you all the bytes in memory in hexadecimal. But the code area, by default in the BIOS, starts at address 202 in hex. And so that's where the code I have just loaded is located right now. If I run that code now, what it will do, it will just create a little typewriter on the screen. That's all. And that's just a simple demonstration of the protocol of communication between CAT, the I/O processor, which reads the keyboard, and the current currently active CPU, in this case the 6502. They communicate to one another via memory mapped I/O. So when a key is pressed, that's the keyboard input, cat here will be interrupted when a key is pressed. It will then pause the CPU, store the result of that keystroke or the value of that keystroke in memory. It will then release the CPU, issue an interrupt to the CPU, telling the CPU, go look in memory because there is something there for you. Then the CPU goes to memory, reads in the value of the key pressed, and that's what you see on the screen. So it's a simple application, but exercising this protocol. Now we can go for, if I press ESC, I just go back to the BIOS screen, and we can load something else. We can load cell6502.bin, and that's a stress test application. It's basically a cellular automaton. The best way to explain this to you is to just run it. I'm in 4 megahertz mode, so we'll be able to see what's happening on the screen. And what's happening there is that this is a Rule 30 cellular automaton. It's a mathematical application. If you type Rule 30 cellular automaton, you get a lot of information on Google. And in addition to running the cellular automaton, the character definition of the one character being used in the automaton is also being updated every time. That's what creates this pulsating effect that you see on the screen. Now, I can step through the code by pressing S, and then that protocol I just explained between the I/O controller and the CPU will happen. I can keep on pressing S so you can see how the character definition is being changed each time. And I can press any other key to let it go again and step it and so on. Now, more interesting is if we go to fast mode, 8 megahertz, and then we run the same code again, and it goes a little faster. In the 6502, however, what you're seeing now is very slow compared to the Z80. And that has to do with the fact that the 6502 it was made to be cheap. It's not really a complete CPU. A lot of the timing protocol that has to be implemented before we can pause the 6502 is actually implemented in the CPLD here, which communicates to the 6502 via a slow PCB. In the Z80, this is all done internally in the die of the Z80. So it goes a lot faster, not to mention the fact that the Z80 has hardware optimized memory transfer units, instructions. It can move entire blocks of memory from one position to the other very quickly because of this hardware optimized instructions like LDIR. So the Z80 is naturally faster for this kind of software scrolling application anyway, but in this case the 6502 has the additional handicap that of a lot of the timing required for this transfer of control protocol is done in the CPLD. And you might ask, well, if I don't press S and let the thing run by itself, no transfer of control is happening. Yeah, but there is still something else. These dual-ported memories, sometimes they are busy. If the 6502 is trying to write into the same address that is being read on the other side by the video circuitry, the memory will issue a pause and will force the 6502 to halt for a little while. But halting the 6502 requires this specific timing protocol. You cannot halt it, or you cannot tri-state its buzzes before it's already halted for at least half a clock cycle, and you cannot unhalt it less than clock cycle after you have halted it. So there's all kinds of things that need to be done here, and which for the Z80 are done here in die. So it's a lot faster. So instead of talking more, let's go to the Z80 and show the equivalent application. And we have to load the new code, cell z80.bin. And if we run it now, the character definitions will not be updated, but that doesn't require many clock cycles anyway. It's just writing 8 bytes to one memory position. Compared to the software scrolling, it's nothing. But you see how fast it goes. It's basically invisible. If I step through it, you see what it's actually doing. But if I let it go, it's so fast. It's faster than the video circuitry. the Z80 will update the frames in memory faster than the video circuitry will read them out. That's why you have this effect. And we can do these little steps so you see that things are actually moving up. They're scrolling up as they should. But if you just let it go, it's impossible to see. We can slow it down. Let's slow it and run again. But even then, it's pretty hard to see. You have a better idea now of what's happening, but it's pretty hard to see. The Z80 has the same type application. Let's look here at the default commands. We have the usual file system commands. I can delete, I can create files on the micro SD card. I can save memory contents to the micro SD card. I can do block transfers in memory. I can test memory. If we do test mem, what it will do, the I/O controller or CAT will write the character, all the character list to the low memory, then it will read from the low memory and write to the high memory, then read from the high memory and write to the video memory, and then at the end we will see the characters on the screen. And this will happen slowly because, again, CAT does not have parallel access to the buses. It has to talk serially to Spacer, and Spacer will use its internal shift registers to translate that serial access into parallel accesses, and that takes quite a lot of time. You have to know it's one clock tick at least for each of the 16 address bits, and then each of the 8 data bits. That's why it goes so slow. If I run it again, you see it's very slow compared to the CPUs. Now, if we list memory, you will see that everything now is in order. In address 0, you have 0, and then 1, 2, 3, 4, 5. And that's what this test memory application does. It will write this, 0 to 255 into the memories, because each one of these 256 numbers corresponds to a different character definition here in the character memory. So that's why you see these numbers there on the screen. If we look at another memory position, say 8000, actually it will write to all the memories. So what we'll do now, let's load an application again. That same application, if I go to now 202, you see that things are more random, because these are the opcodes of the cellular automaton application that I just loaded. But if we now list from 0, it's all ordered, I can now move those blocks, say from 0 to B0. Let's do it B7, 0 to B7. And I will put it now starting on address 202X. And if I go now to address 202, that's what we see, that those values have been copied from the bottom of the memory to address 202 onwards. So you can manipulate memory directly in Cerberus. Actually, I can write to any part of memory directly by typing 0x and then the address. Now let's see, starting at F00, that's the character definitions. And the first character definition is the cursor, the little strong man with a C on his chest. So I can change that one. Let's replace it with alternating lines. FF00, FF00, FF00. And you see that the cursor character will change into 4 horizontal lines. There you are. That's the new cursor, you see. And of course, we can write straight into video memory as well by typing 0x, and then video memory starts at F8. So let's do a little further down the line. Let's do F810, and let's write the cursor character. And there you have it, right on the top. F8, let's do it a little further down, 99, and then 0, 1, 2, 3, 4, 5, 6, 7. And then we get some of these block graphics characters on the screen, all of which I can redefine. So if I go back now to F00 and I change the cursor to a full block, and then that definition will change not only on the cursor itself, but in the places on the screen where I have printed character 0. You see, it's now a full block everywhere. And if you want to go back to where it was, you can either reset or just load the character definitions, which I don't remember how they are called anymore. Char defs, yeah. Load char defs .bin, and then I have to give the address. The character definitions start at F00, and this will reconstitute the cursor character. You see, I have the strong man there again. But since I wrote beyond the borders, if I type CLS, it will clear within the borders, but not the borders themselves. So in this case, it's just faster to reset, soft reset the machine. And there we are. We are back to this screen. And this is pretty much the default functionality, the vanilla functionality you get with Cerberus when you use the default BIOS out of my repository. In the next episodes, I will show you what people have done with Cerberus. They have not only written and ported applications for both the 6502 and the Z80, they've also changed the BIOS to make the BIOS a lot more powerful. To change the BIOS, you just need to connect one of these FTDI adapters right here. And with a little FTDI cable, you can just upload a completely new BIOS, and the BIOS is basically an Arduino sketch written in C. So it doesn't get much easier than that for you to hack the entire machine, and people, of course, went ahead and did that. So in the next episodes, I will show you different versions of the BIOS, more powerful BIOSes, and the stuff, the development team, some very clever guys, 3 very clever guys have been working on the software part of Cerberus. I'll show what they have come up with, including a game, Manic Miner, with high-resolution graphics, including BBC Basic ported to the 6502 and to the Z80, including an entire operating system, Ruby OS, that has been ported to the 6502. All that is coming up. So I will see you then. Take care.